Thanks to the organizers give me this chance. I'm very glad to take this conference. My title is non-existence of perfect binary sequence. My name is Xiaolei from Nanjing Normal University, China. This is a joint work with my professor Hai Cao and Professor Ke Jinfeng. We will introduct my talk in the following three parts: definitions, null results, and our results. First of all, we will introduce some definition. For a binary sequence A0, A1 to A0 -1 with greater n, and for j greater than or equal 0, aj is -1 or 1. The autocorrelation values of A are defined by CAT. T is 0, 1, and 2 n-1. For if T is 0, A by A plus T is 1. So C is 0. So C is 0 is 1 is and it is called trivial autocorrelation value, and the others called non-trivial. For the CAT, there is a simple necessary condition. CAT congruent n model 4. If non-trivial autocorrelation values are equal to some constant d, that is CAT is d. This case we set sequence with two level autocorrelation values. If the non-trivial autocorrelation value d is as small as possible in absolute value, is useful in the communication. So such a sequence is called perfect. There is a relationship between different styles and sequence. Let J is additive group of order n, or K subset D of J is an nk lambda different set. If any non-zero element J in J, there is excited lambda solution D0 such that D minus D0 is J. If J is cyclic, then we set D is cyclic. For example, let J is Z7 and D is 0, 1, 3. It is easy. Check that D is 7, 3, 1 CDS. In 1999, Chemical and Pot gives the relationship between sequence and different style CDS. Let A is A0, A1 to AN-1 be a binary sequence, and J is Zn. When let D is a subset of J, if I is is non-negative 1, we put I in D. So if C AT is D, then we have D is an NK lambda CDS, where D is n minus 4 times n minus lambda. On the other hand, if D is an NK lambda CDS, we can have a binary sequence with C AT is a constant. For example, A is -1, 1, and so on. With N is 13 and D is 1. We construct D 0, 0, 3, 9. So D is 13, 4, 1 CDS. For NK lambda CDS, since K times K minus 1 is equal to N minus 1 lambda, so we have K is this and lambda is this. So since K is encounter, so this is greater than or equal 0. So we have D greater than -2 when N greater than 2, and D is -2 when N is 2. For the later case, there is perfect binary sequence -1, 1. In the following, we consider the first case, N greater than 2 and D greater than -2. For the first case, N congruent 1, model 4, and D is 1. This case, perfect binary sequence, we only consider NK lambda CDS. Now we will introduce some null results. When N is 5 and N is 13, there exists two perfect binary sequence. The others is non-existence. In 1965, prove no perfect binary sequence for N greater than 13, less than 266. Later, this and this in 1992 they prove no perfect binary sequence for N greater than 13 and less than 20 20,000 and 605, but they leave 4 case as open problem. 2 years later, Britain proved the 4 case is not existent, so they have no perfect binary sequence for N greater than 13 and less than 20,000 and 605. Twenty 2016 suite give a conjecture. There is no perfect binary sequence with n greater than 13 and d is 1. Now we will introduce our results. First, we introduce a theorem in 1983 leaders. If A and B are integer, we say A is semi-primitive model B if there exists an interstate such that A to C congruent -1 model B. Let B be a prime for M. VPM is L if and only if P to L is a derivative of M and P to L plus 1 is not. So suppose that there exists an NK lambda CDS, let E is a derivative of N and P is a prime. P is a semi-prime model E, then VP minus lambda is ever. Our idea is that if VPK minus lambda is order, then they are not this CDS, so they are not binary sequence. For this case, we only consider this NK lambda CDS, so that this is U. Then we consider NK lambda CDS. We have our first conclusion. Let U congruent 3 or 7 model 10. They are not this case CDS if one of the following two condition is one, they to use square minus 1 is even, and 2, there is a prime P congruent 2 or 3 or 4 model 5 such that VP U minus 1 or VP U plus 1 is order. For example, let P is 2. We have this case, and let P is 3. We have this case. Perfect binary sequence is not existent. Use the number series. We have our theorem. If there is an U satisfies the following two conditions, U is order and U square concurrent -1 model E, and this case will stay greater than 0, L greater than and or equal 0, and this there are no perfect binary sequence. For example, if E is 5, your congruent plus or minus 7 mod 20 or 55th mod 180, there are no perfect binary sequence. If E is 13, we have this version. For the two cases, N is congruent to model 4 and D is 2. 1999 Janico and Port give the following results. Leave 4 cases as the open problem. We use the algebraic number series give a necessary condition. In this lemma, we use a pair equal to have this completion. So we prove 3 of 4 cases not perfect binary sequence. For the 3 cases, similar the case 1. Similar to case 1, we consider N lambda CDS. So we have our conclusion. And for example, U congruent 27, 45, 51, and 69 model 72. There doesn't no existence of binary sequence. Similar the case 1, we have this condition. And for example, now for this case, similar different size for N concurrent 3, model 4, and U less than 100, we have this conclusion. In the table 1, for 710 is existence, and the others for this case and this case we have no idea, so leave a question. The other case we use the no results candidate. For the for case N computer 0 model 4 and D is 4. If D is 0, this CDS is Hadamard CDS. There are a lot of results about Hadamard CDS, so we consider D is 4. In this case, we similar case 2 use the number series. Number series get this lemma. Use this lemma, we have our conclusion. There is no binary sequence with N not 8 and 40, and D is 4. The following is the reference. Thank you.
Questions for our speaker? Yes.
It looks like those sequences die out, right, for large lengths, and this is you can see that from the theoretical results before your work, but also with what you did with algebraic number theory this valuation of the prime. But there is another definition of perfect binary sequences where the autocorrelations are not all equal, but they can belong to a restricted set. For example, let's say 0 plus minus 2, something like that, right? There is a survey paper by Arasu where you can find this definition. And with this definition, they seem to exist. So my question is, does your technique apply when the autocorrelations are not all equal, but they can be different? It's okay, we can discuss it later on.
Okay. Got about a minute left. Any other questions? All right, let's thank our speaker one more time.